From the smallest grain of sand to the most distant star, everything in the cosmos is built from tiny units known as atoms. Atoms combine to form molecules, materials, and all the wonders of the universe. To grasp the cosmos, we must journey into the heart of matter to understand the structure of atoms. Imagine holding a shimmering diamond. Beneath its surface lies a microscopic realm where atoms interact. This is the world we are about to explore. Our quest to understand the atom begins in ancient Greece, where philosophers like Democritus pondered the nature of matter. Democritus proposed that everything in the universe was made of tiny, indivisible particles he called atomos. John Dalton reintroduced the idea of atoms in the early 1800s. Dalton's theory proposed that each element was composed of unique, indivisible atoms. As scientists delved deeper, they discovered a more complex reality of subatomic particles and quantum phenomena. As scientists developed increasingly sophisticated tools to probe the atom's secrets, they realized that Dalton's model was incomplete. Experiments revealed that atoms were not indivisible spheres, but rather contained smaller, electrically charged particles. This led to the discovery of the atom's core, the nucleus, a tiny, dense region at the center of the atom where most of its mass resides. Imagine the atom as a vast cathedral, with the nucleus as its central altar. The nucleus is incredibly small compared to the overall size of the atom, yet it holds the key to the atom's identity and stability. This tiny, dense core is composed of two types of particles, protons and neutrons, bound together by the strong nuclear force, one of the most powerful forces in the universe. The discovery of the nucleus revolutionized our understanding of the atom, revealing a complex and dynamic structure within these fundamental building blocks of matter. In the bustling metropolis of the atom, protons play a crucial role. These positively charged particles, residing within the nucleus, determine the atom's atomic number, its fundamental identity card in the periodic table of elements. Each element has a unique atomic number, representing the number of protons in its nucleus. For instance, hydrogen, the simplest element, has 1 proton, while carbon, the backbone of life, has 6. Imagine protons as tiny beacons, each emitting a unique signal that identifies the atom to which it belongs. This positive charge also plays a vital role in the atom's interactions with other atoms, influencing its chemical behavior and its ability to form bonds. The number of protons in an atom dictates its chemical properties and its place in the grand scheme of elements. These tiny particles, carrying the blueprint of atomic identity, hold the key to understanding the diversity and complexity of the elements that make up our universe. Section 5. Neutrons. Holding the nucleus together. While protons provide the atom's identity, neutrons, their neutral companions within the nucleus, play a critical role in maintaining the atom's stability. Neutrons, as their name suggests, carry no electrical charge, providing a balancing force to the repulsive forces between the positively charged protons. Without neutrons, the electrostatic repulsion between protons would tear the nucleus apart, leaving the atom in disarray. Imagine neutrons as cosmic glue, binding the nucleus together despite the intense electromagnetic forces at play. The number of neutrons in an atom can vary, giving rise to isotopes, atoms of the same element with different numbers of neutrons. These isotopes exhibit subtle differences in their properties, influencing their behavior in nuclear reactions and their applications in various fields. These neutral particles, often overlooked, play a crucial role in maintaining the delicate balance of forces within the atom, ensuring its stability and allowing the formation of the elements that make up our universe. Section 6. Beyond the nucleus, a cloud of electrons. Venturing beyond the bustling nucleus, we enter the realm of electrons, tiny, negatively charged particles that whiz around the nucleus at incredible speeds. Unlike the well-defined orbits of planets in our solar system, electrons exist in a cloud-like region surrounding the nucleus, their exact positions and momenta governed by the laws of quantum mechanics. Imagine the atom as a miniature solar system, with the nucleus as the sun and electrons as planets orbiting around it. However, unlike our solar system, the electrons' paths are not fixed, but rather exist as a probability cloud, their locations described by wave functions rather than precise trajectories. This quantum fuzziness, a fundamental principle of the subatomic world, challenges our classical intuitions about the nature of particles and their movements. These negatively charged particles, constantly in motion, hold the key to understanding the atom's interactions with other atoms, its chemical behavior, and its role in forming the molecules that make up our world. Section 7. Electrons in orbit shells and energy levels. Electrons, in their frenetic dance around the nucleus, occupy specific energy levels, much like guests choosing floors in a hotel. These energy levels, called electron shells, are quantized, meaning electrons can only exist at specific energy values, not in between. The further an electron is from the nucleus, the higher its energy level. Imagine the atom as a multi-story building with each floor representing an electron shell. Electrons can move between these shells by absorbing or emitting energy in the form of photons, tiny packets of light. When an electron absorbs energy, it jumps to a higher energy level. When it releases energy, it falls back down to a lower level, emitting light in the process. This intricate dance of electrons between energy levels, governed by the laws of quantum mechanics, dictates the atom's interactions with light and its role in various physical and chemical phenomena, from the colors we see to the bonds that hold molecules together. Section 8. The Dance of Charge. How atomic particles interact. The intricate ballet of atomic particles is governed by one of the fundamental forces in the universe, electromagnetism. Protons, with their positive charge, and electrons, with their negative charge, exert attractive forces on each other, much like dancers drawn together in a waltz. This electromagnetic tango between opposite charges is what holds the atom together, preventing the negatively charged electrons from flying off into space. Imagine the atom as a microscopic dance floor with protons and electrons engaged in an intricate waltz, their movements dictated by the invisible forces of electromagnetism. The strength of these forces determines the atom's size, its ionization energy, the energy required to remove an electron, and its affinity for forming bonds with other atoms. This delicate balance of charges, a fundamental principle of electromagnetism, governs the interactions between atoms, influencing their chemical behavior and their ability to form the molecules that make up our world. Section 9. Isotopes, variations on an atomic theme. While the number of protons defines an element's identity, the number of neutrons can vary, giving rise to isotopes, atoms of the same element with different numbers of neutrons. These atomic siblings, while sharing the same chemical properties, exhibit subtle differences in their masses and nuclear stability, influencing their behavior in nuclear reactions and their applications in various fields. Imagine isotopes as different editions of the same book with the same story, chemical properties, but slight variations in the text, number of neutrons. Some isotopes are stable, their nuclei remaining intact indefinitely, while others are radioactive, their nuclei decaying over time, emitting particles and energy in the process. These variations on an atomic theme, with their unique properties and behaviors, play crucial roles in fields ranging from medicine and archaeology to energy production and astrophysics, providing valuable tools for understanding the universe and its intricate workings. Section 10. Why does atomic structure matter? Understanding the structure of atoms is not just an esoteric pursuit for physicists and chemists. It has profound implications for our understanding of the universe and our ability to manipulate matter at its most fundamental level. From the development of new materials and technologies to the diagnosis and treatment of diseases, atomic structure underpins countless aspects of modern science and everyday life. Imagine a world without an understanding of atomic structure. We wouldn't have computers, smartphones, or the internet. Medical imaging techniques like X-rays and MRI scans would be inconceivable. We wouldn't understand the processes that power the stars or the mechanisms of life itself. Atomic structure is the foundation upon which our understanding of the physical world is built. By delving into the atom's secrets, we unlock the secrets of the universe itself, gaining the power to manipulate matter, harness energy, and create new technologies that shape our world. Section 11. Unlocking the secrets of the universe, one atom at a time. Our journey into the heart of the atom reveals astonishing complexity and beauty. From the bustling nucleus where protons and neutrons huddle together, to the ethereal realm of electrons, dancing in their quantum clouds, the atom stands as a testament to the elegance of nature's laws. As we explore the atom's mysteries with sophisticated tools, we unlock new secrets about the universe and our place within it.